Hello. So on my last video, I basically discussed orient you with this 3-bus example, how to do the admittance matrix, and then how are we going to treat the buses, which one is the slack bus or the reference bus. So we choose bus 1, and then bus 2 is a PQ bus. For bus 3, it can be a PQ, it can be a PV, but we'll be using PV bus. And then how to initialize your iteration, how to initialize your load flow solution, and then how to go to load flow from KCL. So that's basically what I did on my previous video. So we end up with this equation. So basically we derive this equation from our KCL, summation of the currents at bus 2. Okay, so I'll just continue with the solution. So what I'll be showing you is the solution for Gauss Seidel. So this is how you do Gauss Seidel. Well, first let's do this equation. Let's solve for the value of this equation. Okay, so what we are saying here is that voltage conjugate of bus 2 times the total current, this one, is equal to the power injection, which is this one. So that's basically like your KCL, but instead of currents, it's in terms of voltage, power, apparent power. Now, if we substitute the values of V2, V1, and V3, V2, V1, V2, of course V3, and the values from the admittance matrix, you'll get this equation. Now we equate this equation into the power injection. So let's look at the power injection first before solving for the left hand side. As you can see, the power injection on bus 2 is from a load, not a generator. So instead of an injection, it's power drawn from the bus. So instead of writing it as 0.3 and 0.4, we write it as a negative injection or a power drawn. So as you can see, that's why when I write this equation, I equated it into a negative 0.3, because instead of a positive injection, it's a negative injection, minus J.4, again because instead of a positive injection, it's a negative injection, it's power drawn. And then you have the conjugate here, so that's this conjugate. So that's basically how you interpret this negative here. That's why it's negative and then minus here. Okay, so then you have this whole term conjugated, so that's why you have a negative 0.3 plus J.4. Now if you solve for this, if you solve for this one, sorry for this one, I made a mistake, so I deleted this. This is not a conjugate, this is just it's just an erasure. Okay, so if you solve for this equation, the top one, you'll get this formula, and that is equated to negative 0.3 plus J.4. Sir, why is these two sides, the left hand side and the right hand side, not equal? That is because for you to solve this, we use these values, and take note, those values are not the solution. These values of V1, V2, and V3, this set is not the solution for you to get this. That is basically the reason why we are doing load flow. We are trying to get the values of the voltages that will allow you to get a negative 0.3 and a plus 0.4 on bus 2. And because V1 that is 1 angle 0, V2 that is 1 angle 0, and V3 that is 1.01 angle 0 is not the solution, you don't get these values. So what do we do? instead of solving for this equation, we can use this to get a better value, of the voltages. So for bus 2, you can isolate this V2 from the left hand side by, of course, you have S injection, divide it by V2 conjugate, so you know how this V2 conjugate here and this side, and then you subtract V1 Y21 to this side, so that you only have V2 Y22 and V3 Y23 here, and subtract this one, so that you'll only left with V2 Y22 on this left hand side, and then divide it by Y22 so that you get V2. Now that is this equation. So now you have a way to approximate a new value for V2 such that all of these values, V2, V1, and V3, are values from the previous iteration, which in this case is iteration 0. So if you substitute those values, you can get a new value for V2, that is 0.96 angle negative 1.78 degrees. So this is now the new value of V2. Now let's use that value in this equation again, in this power equation, in our KCL equation for power. If you use the new value of V2 instead of 1 angle 0, of course we'll still be using 1 angle 0 for V1 and 1.01 angle 0 for V3. We can get we'll still be using this for V1 and this for V3, but we'll use the new value of V2. Solving for this, we can get the left hand side equation to be negative 0.3 plus J 0.4377, and that is still not equal to the power injection on the right hand side. However, these values are a lot closer as compared to the as compared to the previous one, which is just 0 and 0.05. So from here we can say that the 0.96 angle negative 1.78 is an improved value for V2. Well, it's still not good enough, I guess, but it is a lot better than just 1 angle 0. So now you have a value for V2 that is a lot better and a lot closer to the solution as compared to just 1 angle 0. So we can still do the same for bus 3. We can do the same for bus 3. This is your power summation KCL, power KCL on bus 3, and then the equation for that is this one. As you can see, there is actually a pattern for doing the right hand side, and of course the right hand side is just the power injection. There is actually a pattern para hindi na kayo mahirapang i-memorize yung equation. There is a pattern for that. And then you'll end up with almost the same or somewhat familiar equation from V2 for V3. Now take note that for V3, on V3 conjugate, we'll still be using the V3 at the previous iteration because we don't have an improved value of V3 yet. However, for V2, we use the new value because we know that that new value is a better value, is a value that is closer to the real solution. So we now, instead of using 1 angle 0 on V2, we now use the new V2, which is 0.96 angle negative 1.78. So you just do whatever you did on V2. So you still substitute the S injected. Now let's look at the S injected. Let's look at P first. On P, you see a negative 0.2. However, here there is no 0.2. So why? Why is that a negative 0.2? Take note that this S injection particularly pertains to the net injection in the bus. So for the real component, this is 0.3 per unit or 30 megawatts. This is 50 megawatts. So there is a net power. Well, this is 30 that is going into the bus and 50 that is going out of the bus. So there is a net power that is 20 megawatts going out of the bus or 0.2. So since it is going out of the bus, therefore it is a negative injection. Hence the negative sign. Now, sir, why is this JQ? Why not use 0.5? Take note that this is PV bus. Now, as I have told you before, for a PV bus, what you want to happen is you want to force the network to have that certain P and that certain V. So that's basically the reason why you called it PV bus. You want to have it you want to force the network to have a certain P injection on that bus. In this case, this is a negative 0.2 or negative 20 megawatts or 20 megawatts going out of the bus. And you want to force it to have a certain voltage, which in this case is 1.01. And that is at the expense of having a variable Q and variable voltage angle. That's different for PQ bus, because for PQ bus, you want to force the network to have a certain P and a certain Q. And that is at the expense of variable voltage magnitude and voltage angle. That's why, as you can see on bus 2, both our voltage magnitude and voltage angle changed from 1 angle 0 to 0.96 angle negative 1.7. So for PV bus, you want to make the voltage magnitude constant and the power injection constant. So that is at the expense of a variable Q. So therefore, you cannot make this Q 0.5 because our Q here is variable for you to have 1.01 magnitude. So how do we know Q? So we can get the value of the reactive power from this left-hand side. We can get the value of the reactive power from this left-hand side. Take note that this left-hand side is the formula for power. So, and that power is S. It's made up of P and Q. So you just get the imaginary component of that. Then you get Q. So for Q, you may use this formula. Take note, this is positive imaginary of V3 times all of the I's conjugate. So it's basically VI conjugate. Or negative imaginary of V conjugate I, which is basically this formula. It's V conjugate I. So we may use negative imaginary of V conjugate I. So if you solve for this equation, if you solve for this equation, you end up with this, and to get the negative imaginary, it is 0.2775. So instead of substituting 0.5 here, you substitute instead of putting a 0.5 there, you substitute 0.27775. And from that, from this equation, from this equation, using 0.27775, you get this value for voltage. Now, take note that this is a PV bus. Therefore, our interest for this value of voltage is on the angle only, because we know that its magnitude is, well, because we are forcing its magnitude to be 1.01. So it's just 1.01 angle whatever is this angle, negative 1.97. So for the first iteration, that's basically the end of the first iteration, you just get you have this value for voltages. Now if you compute for the discrepancies of the voltages, this one, the discrepancy of the voltages after the first iteration is just the voltages at the first iteration minus the voltages on the previous iteration. In this case are initialized values, so you just get the magnitude of that after don't get the magnitude first then subtract. You must get the difference first and then get the magnitudes. So it's basically the magnitudes of the errors, not the error of the magnitudes. Yeah. Okay. Anyways, so this is the errors. This basically tells you how much did the values of the voltages change. So this voltage discrepancy can be compared into a certain tolerance level to know if the error is acceptable. Let's say, for example, if you have if you set a value of tolerance that is 0.05, that is, you want an error to be less than or equal to 0.05, then all of these voltages, all of these errors are less than 0.05. Then I guess on that tolerance, these values of voltages, these new values of voltages, where is that? This one is already acceptable on 0.05 tolerance. If you set a tolerance of 0.04, if you set a tolerance of 0.04, then you only have V1 and V3 satisfying the set tolerance. So since V2 is not yet satisfactory on the set tolerance that is 0.04, then we perform another iteration, not just for V2 but for all of the bus voltages. Well, the tendency is all of your buses will just have a smaller error, and then V2 will have a smaller error, and then hopefully it will be below than the set tolerance, and then all of them are now acceptable. So again, if you perform another iteration, you don't just perform it on V2, you perform it on all of the buses. You perform all of the buses and then compute again for the errors of all of them. So I do this in MATLAB, and then I set an error of 10 raised to negative 6. So it's 5 zeros before 1 after the decimal place. So for that error, I reached 8 iterations, and then I have these voltages. So yeah, I have these voltages. So you may use these voltages. Yeah, you may use these voltages on sorry. You may use those voltages on this equation, and then it's a lot closer to this, to the S injection. It may not be exactly equal, it may not be exactly negative 0.3 plus J.4, but it's very much close to that. And then you may use those for this. Where is that? Yeah, this one. You may use those for those values for these voltages, and then it will be close to negative 0.2. Take note, it may be far from negative 0.5 because again we set it may be far from negative J.5, positive J.5, yes, because of the conjugate, because we set bus 3 to be PV. So that means we are not monitoring the value of Q. Okay, but the voltages are this is the solution for the voltages, for you to have that power flow. No, Yeah, that power injections, yes. Okay, so I guess that's it for Gauss Seidel.